Welcome to AI Paper Slop, the YouTube series where we extract the core signal from the noise of the latest AI and ML research. Today we're jumping straight into a massive one. It's called Parametric Skills by Xuan Zhao, Honan He, Qingyu Yang, and their colleagues from the Shanghai AI Lab and others.
Yeah, this is a big one.
Right. And here is the rapid-fire summary of what you need to know right off the bat. This paper proposes a framework to convert free-form textual skills directly into continuous LoRA adapters at test time, and they do this using a hypernetwork.
Which is wild.
It is. It completely eliminates the context window overhead of traditional in-context skill learning. So it basically solves that lost-in-the-middle problem for agentic tasks. It allows for context-free skill exploitation and achieves a 6.44-point increase over in-context learning on complex software engineering tasks, as judged by DeepSeek V4 Flash.
And, for you listening, whether you're an AI practitioner or an ML engineer, this represents a really fundamental shift in how we think about agentic workflows.
Because we've been doing it the hard way, right?
Exactly. For the last couple of years, the default method for giving an agent a new skill has been, just shoving massive text documents into a model's prompt.
Just huge context blocks.
Yeah, huge. But we are moving away from that text-based paradigm entirely here. We're moving directly into parameter space. This paper basically proves that compiling textual skills directly into the model's weights on the fly is significantly more effective than, asking a model to read its own instructions at inference time.
I like to imagine it like forcing a master chef to read a dense 50-page recipe manual every single time they chop an onion or deglaze a pan.
That would be a nightmare.
Right. That is essentially what we are doing to large language models today. They have to process the task, the environment state, and this massive text-based instruction manual all simultaneously. Naturally, they just lose their place.
They hallucinate an API call from page 42 because their attention heads are just spread way too thin across that massive context window.
Exactly. But before we get into the hypernetwork architecture, we need to look at why evolving skills in text space is, fundamentally decoupled from actual machine learning.
Well, if you look at current self-evolving agent frameworks like EvoSkill or SkillUp, they operate on a really specific loop.
Where the prompt just gets longer and longer.
Yes. The agent fails a task, a verifier notes the failure, and then an LLM rewrites the natural language prompt to be slightly better for the next attempt. So the instruction manual gets longer, more specific, and frankly, just wordier.
But the model's actual weights, like its intrinsic neural pathways, those remain completely untouched.
Untouched. The model itself isn't learning a single thing.
The prompt is getting smarter, but the brain is staying exactly the same. And I've noticed this gap between fine-tuning and in-context learning seems to widen really sharply as model size decreases.
Oh, it definitely.
Like they use Qwen38B as their backbone in this paper, and smaller open source models just choke on multi-step procedural logic when it's wrapped in dense text.
Yeah, whereas massive proprietary models can sometimes just brute force their way through it.
Right. Why is that drop-off so sharp for the smaller models?
It comes down to raw attention capacity. A massive frontier model has the sheer number of attention heads to juggle task, context, system state, and procedural instructions all at once.
Okay, that makes sense.
An 8 billion parameter model absolutely has the latent capability to execute complex software engineering tasks if its weights are properly aligned to do so.
But it lacks the bandwidth?
Exactly. It lacks the attention bandwidth to dynamically extract that procedure from a dense text prompt while it's also tracking the state of a really messy terminal environment.
So the goal is to get the knowledge out of the prompt and bake it directly into the weights. And that brings us to the core mechanism of the paper.
A hypernetwork.
The hypernetwork, yeah, which they use for their text-to-LoRA architecture. For anyone listening who might be unfamiliar, a hypernetwork is basically a neural network whose entire job is to generate the weights for another neural network.
Which sounds like sci-fi, but it works.
It really does. But how are they actually mapping an English text document into a low-rank adaptation matrix, practically speaking?
So the anatomy of this parametric skills mechanism starts with a frozen text encoder. They feed the natural language skill document, say, a guide on how to patch a specific database into this encoder.
Okay, so just standard encoding so far.
Right. The encoder embeds the entire document into a continuous, dense vector representation. They call this vector Z. Then the hypernetwork takes over.
And what does it do with Z?
It takes Z and projects it through multi-layer perceptrons to generate the flattened parameters of a LoRA module. Specifically, it outputs the values for the A and B matrices of the LoRA array.
Wow.
Yeah, and then those matrices are reshaped and injected directly into the frozen base model, which, like you mentioned, is Qwen 38B here.
It's like that scene in The Matrix where Neo gets Kung Fu downloaded directly into his brain.
That is actually the perfect analogy.
Right, like instead of handing Neo a textbook on martial arts and asking him to read it while fighting, the Hypernetwork just downloads the procedural muscle memory directly into his parameter space.
Yes.
But wait, I have to push back here. If I'm building a real-time agentic system for a production environment, I am extremely paranoid about latency.
Sure. Latency is always the killer.
Right. So if I have an agent trying to act in a live terminal, asking a secondary neural network to hallucinate millions of weights and inject them before I can even run my first LLM forward pass, I mean, that sounds like an inference nightmare.
I know it sounds computationally heavy on paper, but it's actually vastly more efficient than the alternative.
Really? How so?
Because generating the LoRA requires only a single forward pass through the hypernetwork. The math there is just a deterministic series of matrix multiplications.
So no backprop.
No expensive gradient updates at all, and you don't run backpropagation of the base model. Once that LoRA is generated, which is a process that takes literally milliseconds, you inject it, and your LLM inference is incredibly fast.
Because you've completely zeroed out the context window consumption for the skill.
Exactly. It's the exact opposite of traditional prompt engineering.
Because instead of recalculating attention over thousands of tokens of skill instructions at every single step, your prompt is now strictly limited to the task itself and the current environment state.
Right, you pay a tiny one-time fixed cost to generate the adapter, and you save massive amounts of compute on the KV cache during the actual agent execution.
Okay, that makes sense. But a hypernetwork isn't magic, right? It's only as good as the data used to train it.
Oh, absolutely. The data is everything.
The authors are asking a network to learn how to compress highly specific procedural English text into abstract mathematical weight updates. To train that, you'd need an unbelievable amount of highly structured data.
You really would.
And I imagine there isn't a pre-existing data set of like perfect text-to-weight agent behaviors just sitting on Hugging Face.
There wasn't, which is why the data curation effort in this paper is a massive contribution on its own. The researchers actually constructed a library of 45.8K high-quality skills.
Almost 46,000 skills.
Yeah, spanning 13 domains. About 26% is software engineering, 14% is AI and LLM operations, but they also cover DevOps, security, data analysis.
That's a huge spread. How did they even source all that?
They built it by mining two entirely different types of sources.
Let me guess. Explicit documentation, like API docs, and then implicit behaviors.
You nailed it. The explicit docs are the low-hanging fruit, so crawling GitHub repositories, NPM packages, and developer platforms to extract stated skills.
Okay, but what about the implicit ones?
The implicit skills are where the real value lies. They took logs of agents successfully solving real repository-level software problems in multi-turn editing sessions.
So just messy terminal logs?
Exactly. Messy terminal logs showing an agent trying something, failing, inspecting the environment, and eventually finding the solution. The researchers then reverse engineered the underlying procedural skills from those successful trajectories.
But it sounds incredibly noisy. Like you can't just feed raw terminal output and a bunch of print statements into a hypernetwork and expect it to learn generalized coding skills.
No, you just get garbage out.
It would just overfit to fixing a specific bug in one random developer's code base. So how did they clean that up?
They implemented a really rigid summarize, extract, and validate pipeline. First, an LLM compresses the messy trajectory into a highly structured JSON format.
Oh, smart. So it isolates the actual problem localization step.
Yes, it isolates the problem localization and the code inspection strategies used. Then it extracts candidate skills. Finally, and this is the most important part, it validates them in isolated sandbox environments to ensure cross-repository transferability.
So if a skill only works on one specific GitHub issue, it gets thrown out.
Exactly. The hypernetwork has to be trained on generalized procedural knowledge, not just memorized fixes.
Which brings us to the actual training of the hypernetwork. Because if we just train a hypernetwork to memorize text and spit out weights, it's going to fail in the real world where conditions actually change.
Right, which is why they designed a 3-stage curriculum.
I saw that. The first phase focuses on reconstruction. But they do something incredibly clever here. They don't just ask the model to recreate the whole text. They use a closed-style task for section-level component completion.
Yeah, this is a brilliant way to force the Hypernetwork to learn the internal logic of the skills.
How does it work in practice?
Instead of giving the Hypernetwork the full skill document, they randomly delete a crucial functional section, like, say, the failure handling block of an API manual.
Okay.
The Hypernetwork receives the remaining text plus a tag indicating which section is missing. It then has to generate a parametric skill, a LoRA, that allows the base LLM to perfectly infer those missing parameters and execute the task strictly based on the surrounding setup text.
That is wild. It's forcing bidirectional reasoning over the logic of the code.
Exactly.
Like, if you delete the error handling, the Hypernetwork has to mathematically deduce what that error handling should have been, based entirely on the triggering conditions and the execution procedures that are still visible.
Right. It guarantees the network isn't just memorizing strings of text, but is actually mapping the causal relationships of the skill into the parameter space.
That creates a very strong inductive bias for compositional generalization.
It does. But understanding a skill in a vacuum isn't enough. In the next phase of training, they force the model to apply these skills in noisy environments.
Oh, so single-turn skill exploitation.
Yes. They generated over 134,000 instances of realistic repository-level tasks, and they intentionally injected distractors into the prompts.
Like what kind of distractors?
Things like obsolete terminal commands, misleading file locations, or entirely irrelevant bug reports.
Because real-world software engineering is just a mess of red herrings. So if you're relying on a Hypernetwork to generate your weights, those weights need to make the LLM robust against hallucinations. The generated LoRA essentially acts as a set of blinders, keeping the base model laser-focused on the core skill execution despite the noisy context it's reading.
That's a great way to put it. And then they cap the training off with a multi-turn sandbox simulation.
Using OpenCode, right?
Yes, OpenCode allows them to simulate the step-by-step problem-solving process. Real agentic workflows aren't single-turn prompt and responses. They are long conversations where constraints and errors are revealed progressively.
So the Hypernetwork learns to generate parametric skills that maintain coherence across these long horizons.
Exactly. The agent has to plan, modify files, run tests, and verify results, all guided by the parameter space it was injected with at the very start of the task.
Okay, let's talk about deployment realities. In any meaningful SWE task, you rarely use just one skill.
Never just one.
Right, you usually have to stack them. If I'm building a web app, I might need the Hypernetwork to dynamically generate an API routing skill LoRA and simultaneously generate a database patching skill LoRA.
Sure.
If I just take those two generated matrices and add them together, like basic factor-wise linear addition, don't their latent spaces just collide and turn into mathematical soup?
They absolutely do.
Yeah.
Simply adding the weights together destroys the independent linear subspaces that each skill learned.
So they just overwrite each other.
Pretty much.
Yeah.
The representations override each other and performance degrades severely. The authors actually tested this. A basic linear merge scored only a 56.15 on their benchmark.
Ouch. So what's their solution to this collision problem?
Rank concatenation.
Okay, so instead of trying to squash them into the same dimensional space, how does rank concatenation preserve them?
Instead of adding the matrices, they concatenate the low rank factors of all the selected adapters along the rank dimension.
Can you give me an example?
Yeah, so if LoRA A has a rank of 8 and LoRA B has a rank of 8, rank concatenation places them side by side to create a new adapter with a rank of 16.
Oh, so the mathematical operations remain mathematically isolated during the forward pass.
Exactly. But there is a secondary problem here. What happens if one skill naturally requires massive weight updates and the other requires very subtle weight updates?
The loud skill would completely drown out the quiet one.
Right.
It would be a catastrophic forgetting event for the subtle skill just because its numerical magnitudes were lower.
Precisely why they introduce a calibration step before the concatenation. They measure the Frobenius norm of each adapter's effective update.
Okay, for the listener, the Frobenius norm is essentially a measure of the magnitude or like volume of a matrix, right?
Yes, exactly. So by normalizing each adapter based on its Frobenius norm, they ensure that a high magnitude skill doesn't accidentally dominate the entire base model.
Yep.
Both skills contribute proportionally to the final combined LoRA.
And did that fix the scoring drop?
It did. This specific merging technique pushed their benchmark score up to 60.12, completely validating the approach.
Which brings us to what I think is the most exciting application of this framework for anyone listening who manages ML pipelines.
Continual learning.
Yes. solving continual learning without backpropagation. The paper outlines a self-evolving loop at test time. The model faces a task, generates an initial text skill, and the Hypernetwork converts it to a parametric array.
Right.
Then the LLM attempts the task. If it fails, the verifier sends feedback, the model revises the text skill, and the Hypernetwork recompiles it into a brand new array in milliseconds. It just loops until the bug is fixed.
The real value is what happens after the bug is fixed.
Yeah.
When a skill is finally accepted as successful, it isn't just thrown away or stored in a massive, unsearchable text database.
So what do you do with it?
The successful parametric skill is normalized and merged into a global parametric skill using an exponential moving average, or EMA, with a beta of 0.1.
Okay, for those unfamiliar with the EMA application here, a beta of 0.1 means the global parametric skill retains 90% of its previous accumulated knowledge and smoothly absorbs 10% of the new successful skill's weight updates.
Exactly.
So you are essentially creating a reusable memory prior distilled from successful trajectories. Every time your agent solves a new type of edge case in production, it compiles that success into a LoRA, folds it into the global state, and your system gets permanently smarter.
It totally changes the economics of deploying autonomous agents. You don't need to spin up a massive cluster of A100s to run fine-tuning jobs every weekend to teach your model what it learned during the week.
Right. The model improves at test time organically with basically negligible compute overhead.
And the architecture is elegant, and the data pipeline is obviously rigorous, but we should look at if it actually moves the needle when graded by an impartial judge.
Let's look at the empirical results on complex software engineering subtasks. They used DeepSeek V4 Flash to judge the semantic correctness of the agent's outputs.
The numbers are pretty stark. They established a baseline model, just the Quinn backbone, with absolutely no skills injected, which scored a 50.21.
Oh, yeah.
When they provided that same model with standard in-context textual skills, essentially giving the prompt engineering treatment, the score jumped to 57.65.
Standard prompt engineering works, we know that. But where did parametric skills land?
Parametric skills achieved an average score of 64.09.
Wow.
Yeah, it beat the in-context baseline by over 6.4 points. We also saw F1 scores jump by over 5.5%.
That's huge.
And when tested on the classic human-evolved coding benchmark, agents using self-evolved parametric skills achieved an impressive 84.76% pass rate, successfully solving 139 out of 164 problems.
I want to highlight a fascinating detail buried in those baseline comparisons, too. The authors tested another model called Shine.
Ah, yeah.
Shine is a concurrent text-to-LoRA hypernetwork model. Architecturally, it's built to do essentially the exact same thing, map context to weights in a single pass. But when they applied Shine to these complex software engineering tasks, it completely failed.
Yeah, it scored a 48.48.
It performed worse than the raw baseline model that had no skills at all. Why did a fundamentally similar architecture fail so spectacularly?
Because it proves that the Hypernetwork architecture is just a vessel. You can't just plug a text-to-weights model into your pipeline, feed it raw text, and expect magic.
It needs the curriculum.
Exactly. Shine failed because it lacked the rigorous training regimen required to compress operational methodology into weights. The specific three-stage pipeline designed in this paper, the clue-style section deletion that forces bidirectional reasoning, the noise-injected data, the multi-turn sandbox trajectories, that is the actual secret sauce.
So without that curriculum, a hypernetwork just generates mathematical noise.
Precisely.
So what does this mean for you as you look at your own deployments? If you are building agentic systems that rely on massive vector databases of SOPs, coding guidelines, or API manuals, you're currently paying a massive context tax at every single inference step.
And more importantly, you are artificially capping your model's performance by bottlenecking it through its in-context reasoning bandwidth.
This paper offers a tangible blueprint to offload that procedural knowledge directly into the weights, making your agents faster, cheaper, and objectively more capable of handling multi-turn complexity without forgetting what they were doing on step one.
We are definitely moving past the era of just prompting agents. We are entering an era of compiling behaviors into them dynamically. The plug-and-play nature of these LoRAs, especially with rank concatenation, means you can build modular, composable AI systems that continually learn from their successes in the wild.
Entirely bypassing the need for an optimizer step.
Exactly.
Well, I want to leave you with a final, somewhat provocative concept to mull over before we wrap. Right now, this framework takes human-readable text, GitHub README's standard operating procedures, and uses a hypernetwork to compress that language into continuous parameter space. It's a translation bridge between human text and machine weights. But if this self-evolving loop is completely automated, what happens when our systems start generating alien parametric skills?
Oh, wow.
I'm talking about skills that don't originate from human text at all, but are raw, hyper-optimized matrices distilled directly from an agent's own trial and error in a sandbox.
That's a crazy thought.
Could future AI agents begin trading these raw, parameterized skills directly with one another over a network? Imagine a swarm of agents perfectly transferring complex procedural knowledge to each other in milliseconds, entirely bypassing human language, text files, and human comprehension altogether.
It's definitely something to think about as this technology scales.
That's all for this deep dive on AI paper slop. Keep building, and we'll catch you next time.